Hello, everybody. Thank you very much. It's a pleasure to be here celebrating Dustin. It's a wonderful occasion. I'm going to start by what I do essentially in every talk that I start, which is apologizing for my handwriting. Please stop me if there's anything unclear mathematically or typographically. And feel free to ask questions. So I would like to start with a motivating problem. And here's what our motivating problem is going to be. So a natural question in homotopy theory is, what are the homotopy groups of spheres? Homotopy groups are basic invariants in algebraic topology, and the spheres are kind of the basic building blocks of spaces. So that's a very basic question. We know that those are 0 when k is smaller than n. They're equal to z when k equals n. So already maybe that suggests the following change of coordinates, definitely harmless change of coordinates. Let me consider the k plus n homotopy group of Sn. We have here a two-parameter family of groups, but in fact, fundamental suspension theorem tells us that when n is bigger than k plus 1, this thing stabilizes, so it becomes independent of n. Okay? So the moment that the number n here is large enough, this thing is independent of n, so we actually get a one-parameter family that we can consider. Those are known as the stable homotopy group of spheres. So this is going to be defined as this in that range. Okay? So what do we know about it? Well, as I just said, if this number is smaller than this number, it's 0. So what it means is that when k is negative, this stable value is 0. Pi n of Sn is z, so when k equals 0, this is z. And the motivating problem would be understanding what happens when k is positive. And we already know, thanks to Serre, that those are all finite abelian groups. So abelian is before Serre. So we get a sequence of finite abelian groups, one for every positive integer. And, well, for the sake of time, I'm not going to give you the, I'm not going to write on the board a lot of them, but I can tell you that if you just look at the list, at first glance, there seems to be no rhyme or reason. So you have some kind of a sequence of abelian groups that seems to have some kind of a very complex behavior and pattern. Another thing I want to mention is that, generally speaking, computing the precise values of those abelian groups is a non-trivial problem. So until about 6 or 7 years ago, I think, the value of those groups were only known up to K56 or something of so, and then relatively recently by Jolichoux and Dan Isaacson, I believe, pushed it all the way up to above 90 or something. But this is kind of a one-by-one process. It's so this kind of a approach is not the one that we're going to take. We're going to try to find some kind of a more systematic patterns in what's happening here. It's not going to give us the entire picture, but it's going to give us something. I should also mention that, I think being the stable values of the homotopy group of spheres is enough of a motivation, but those homotopy groups actually appear in a lot of other interesting mathematical questions. for example, understanding what they are is essentially the same as understanding what are the classifying smooth structures on n-dimensional spheres. So, thanks to Milnor, we know that there can be more than one smooth structure on the topological manifold, which is the sphere, and the collection of such structure constitute a group. And for dimensions 5 and above, this is essentially controlled by this question as well. So, okay, so that's going to be our motivating problem. And now I'm going to put this problem aside for a second, and I'm going to put this problem into a larger theoretical framework that maybe at first seems less related. And we're going to use this framework to decompose this question into simpler pieces and learn something about it. This kind of a process of taking a concrete problem and embedding it in a complex theoretical structure is something that I sometimes find myself having to apologize for in talks. I have the feeling that in Paris is not one of those places, so I'm just going to continue without apologizing. So the notion that we're going to use is the notion of a spectrum. And what is spectrum? So spectrum for us is going to be defined as a sequence of pointed topological spaces. So topological spaces, one for every integer with a chosen base point, together with a family of equivalences, and by that I mean homotopy equivalences between the n space in the sequence and the based path space of the space after that. So if this is xn plus 1, it has a base point, and I'm considering the space of all loops that start at n in the base point using the, let's say, open compact topology. And I ask for maps like so, and those maps don't need to be a homomorphisms, but I want them to be a homotopy equivalence to define isomorphism on all homotopy groups. Now, once again, if I'm thinking about homotopy groups, I have a family of spaces here, and I can consider the k homotopy group of the xn space, and I'm going to do the same change of coordinate. So via this map Fn, this is going to be the same as the k plus n homotopy group of this loop. And this operation of taking the base loop space, what it does on homotopy groups is just move them one step down, right? So for example, if we consider the connected components of this space, those are just loops up to homotopy. So this is pi 1. So this is continuous for all higher homotopy groups. So this is the same as kn plus 1, xn plus 1. So what we learn is that those homotopy groups depend only on the difference between those two numbers. So once again, I only need to consider one parameter here. And if I take this big family, the spectrum as a mathematical structure and denote it by this fancy x, then I can define its k homotopy group to be the k plus n homotopy group of xn. And this definition, I don't need to specify n because any n will do. I'm going to get the same answer. But that means that this thing is well defined also when k is negative. Because if I take
n bigger than minus k or minus k.
Yeah, so I'm going to change n to be bigger than minus k plus 2, in fact. And the reason I'm going to do that is because I want this to not be only well defined, but also notice that it's abelian. So I can because I can assume that n is as large as I want.
Then you need 2 is enough for abelian.
Yeah.
So bigger than or equal to minus k.
Yes, that's true. So what do I learn? I learn that the homotopy groups of a spectrum are all abelian, and they're indexed by the integers. Other questions? Okay. So So those mathematical objects are spectra. I think they have a little bit of a funny definition. Like, you know, there's kind of mathematical objects that you hear about the definition and kind of you immediately guess what they're trying to encode. And at least for me, that wasn't the case with spectra. It seemed a little bit of a weird structure to look at. And to be honest, the definition is not going to play a role at all in my talk. I'm just giving it because you know, I feel it's better. It's more polite when you're giving a talk and there's a mathematical object which you spend most of the talk working with to give a formal definition. But this formal definition is not going to appear at all in anything that I'm going to do. And instead, I'm going to tell you how I like to think about spectra, or you know, not only me, how we usually think about them. And that way of thinking about them would be the thing that would guide us best for understanding what we're doing. And it's via the following analogy. So spectra to spaces, and by spaces, maybe I should say, you know, this is, we're honoring Dustin here, so maybe I should say anima. I mean spaces up to homotopy. Okay, I don't mean not topological spaces in the classic in that sense, but only the homotopy information of them are the same as abelian groups are to sets. So if you take, you know, this notion of a topological space up to homotopy, and you're adding to it the ability to sum and to take inverses, that's essentially, you come up essentially with the definition of a spectrum. And I'm going to make that claim imprecise, but I'm going to use it to guide the rest of what we're doing. So for me, you know, a spectrum is some kind of a wobbly space, such that I know that every time that I have a map from a finite set, I can make sense of the sum. And that's another point here, and that is coherent, behave the way you would expect addition to behave. Okay?
Do you consider only nice spaces like homotopic to CW complexes, or is there a good theory without this assumption?
Everything is defined up to weak homotopy equivalence, which means that you can restrict yourself to CW or not, and then it will be replaced by one.
Okay, you didn't say weak, you said homotopy equivalent.
Oh, weak homotopy equivalence. Yes. So yeah, those are really anima. Those are not topological spaces. Okay, so that's the analogy that we want to follow. So, well, in what way we're going to follow this analogy? So, the abelian group, the collection of all abelian groups comes together to be a category. And the same thing is true for spectra. And spectra are actually kind of a fancier objects. They organize themselves to an infinity category, but we shouldn't worry about that too much. Now, in the category we're thinking about, the category of abelian groups, we're thinking about homomorphism, linear maps. But if we want to start doing more complex things with abelian group, if we want to start doing algebra, which is where I'm going, we want to consider multilinear maps as well. For example, multiplication of a ring is a multilinear map. And a way to encode multilinear maps is by the fact that we have a tensor product. And well, in the world of spectra, we also have a tensor product that encodes multilinear maps. And this is known as the smash product. But I'm going to denote it exactly the same way to evoke this analogy. This tensor product admits a unit, which is the integers. And there's also a unit here, which is known as the sphere spectrum. Further, well, you know, an abelian group, talking about the relationship between abelian group to sets, well, every abelian group has an underlying set. And this forgetful functor is a left adjoint, which sends a set to the free abelian group generated from it. And exactly the same, if we could, well, denote by S spaces, then we have kind of an underline space, and there's a left adjoint, which we're going to denote by this. This is not a standard notation, but again, I want to evoke this analogy. I'm not a big fan of the standard notations.
Yes, I know. So because I mean this Eilenberg claims, I mean this embedding somehow, how to say that? I mean when you smash product to abelian groups, I mean, and because you are using the same notation, there is an ambiguity if you.
You're right. So what you're referring to, what you're referring to is that I'm writing this as an analogy, but it's more than an analogy. Abelian groups faithfully embed into spectra. That's right. And I think what you're referring to is the fact that this embedding, although fully faithful, is not symmetric monoidal. So if my goal was to kind of think about abelian groups in here, there's supposedly an issue. But I'm not going to think about this embedding a lot. I'm just going to use an analogy. So I don't think it's going to cause us a lot of trouble. But that's right. If I can consider the fully faithful embedding, and then the tensor, this functor is not symmetric monoidal. It doesn't preserve the tensor structure.
Do you do it with spaces or pointed spaces?
You can do either, similar to how you can go back to pointed sets. But I'm actually writing spaces here. I'm thinking about the case of spaces. I just forget the base point.
Okay, so it is the suspension of x plus.
It is the suspension affinity of x plus. That's exactly right. And well, this functor sends this functor in this direction is symmetric monoidal. In particular, it sends the product, a product to a tensor product. So in particular, Z itself is just a free abelian group on a point. And similarly, this functor is symmetric monoidal, and the sphere spectrum itself is a sphere spectrum on a point. Because there is the free, it's a free spectrum on a point. And now, what does all of this has to do with our original motivating problem? Well, this is a spectrum. It's clearly a very important spectrum. It's the unit object in this category. So we can ask, what is its homotopy groups in the sense over there? And those are exactly the stable homotopy groups of spheres. And if you want, it will be historically false, but you could have considered as another motivation to understand the sequence of abelian groups. If you start by, you can imagine a world in which people discovered this infinity or animated world and tried to understand what abelian groups are in this world and invented spectra and found the unit and looked at its homotopy groups before they understood Frunetal suspension theorem. And then this would also come naturally as a problem in natural problem understanding spectra. Just comes up very naturally. Are there any questions so far? How am I going to work this? Okay. So what does all of this structure give us? It gives us an interface in the world of spectra, which is analog to the world of abelian group in a way that allows you to do algebra. So you can start kind of redeveloping the theory of algebra and studying algebraic structures, where the bedrock of this algebra are not abelian groups, in the way that rings are abelian groups with essential additional structures, and Lie algebras are abelian group with additional structure, etc., etc. Modules are abelian group with additional structures. You can start redoing this story in the world of spectra, and you get what is known as, well, what Waldhausen called brave new algebra. And that has been, this perspective has been very successful in both learning things about spectra, but also in kind of shedding light back on the story of abelian group, in particular via this embedding that was mentioned. There can be many interesting spectra that someone want to study. A lot of interesting problems can be encoded as asking what are the homotopy groups or what is the behavior of a given spectrum. For example, algebraic K groups are essentially the homotopy groups of a certain spectrum. Cobordism classes of manifolds are classified as homotopy groups of a spectrum. That's the way originally René Thom computed them. There's relatively recently, Hopkins and Fried showed that certain phases of condensed matter are classified as homotopy groups of spectra. So this is a natural question to ask, but we're interested in this one, in this specific case. And let me now do a slight modification, which is we know because of Serre's work that when K positive, all of those are finite abelian groups. And when we want to understand finite abelian groups, there's a very kind of first basic process that we natural to do, which is work at a given prime. Let's just take the P primary part. There's no real interaction between different primes when we think about finite abelian groups. So we can replace our motivating problem. We're going to kind of fix some prime P for now and forever, and we can consider the P completion of this abelian group and study that instead. And one of the tools that this analogy allows you to do is to realize that actually this process can be lifted to the world of spectra. So there's another spectrum called the P-complete sphere, which you should think of as just the completion, the P-completion of that one in the appropriate sense, whose homotopy groups are just the P-completion of that. So that thing is 0 when K is smaller than 0, it's ZP when K is 0, and it's a finite abelian P group. K is positive. Okay, so and now also let me do a little bit of an abuse notation. Let me call the P-complete sphere just a sphere, and remember that everything is P-completed, just to avoid notational clutter. So we will understand this guy, and Z here is not just an abelian group; it's a commutative ring, and that is closely connected to the fact that it's the unit of this tensor structure, right? Because there's an obvious multiplication map, for example, from Z tensor Z to Z. It's just essentially the isomorphism that comes from the fact that it's the identity. So from the same kind of a formal reason, the sphere is also a commutative ring in the appropriate sense. And what kind of effect that has on the homotopy groups? It means that the homotopy groups are skew commutative rings. So there's a composition map like so, and it is graded commutative in the sense that it commutes unless K and D are both odd, and then it's anti-commutes. So we want to think about this guy as a ring, and how do we study commutative ring? Well, a very powerful approach is the one suggested by algebraic geometry, that kind of says that every time we find ourselves in the presence of a commutative ring, we should imagine that this is in fact, this commutative ring is the ring of functions on some space. And now not space in that sense, but in some other sense, which maybe is vaguer. So if we have a commutative ring, and we think about the space this commutative ring is a function on, if we have an element in this ring, we can consider where this function is 0 and where this function is non-zero. And that suggests a way to decompose the space into two pieces, and in appropriate way also, in some sense, decompose our ring into two simpler pieces that then maybe we can glue together. So this suggests some kind of a divide and conquer. And what is the ring that we're going to get as the functions essentially where f is non-zero? Well, that's going to be what happens if you invert f on the ring R. And here, we're going to get R mod f. And essentially, for most f's that we're going to choose for in kind of a random ring, this is going to give us two two pieces, but not always, right? So one thing that can happen that if f is invertible, then if f is invertible, then doing this is going to give us 0, and inverting not going to do anything. So that just means that we didn't really decompose the space. The function is always non-zero. Another option is that f is, let's say, nilpotent. So if f is nilpotent, inverting f kills it. So there's really nothing happening here. And on this side, well, maybe we change a little bit, but somehow the geometry didn't change. So unless every element in the ring is either nilpotent or invertible, we can kind of break it into two pieces in an interesting way. But there are rings for which every element is either nilpotent or invertible. So one example is fields, like F5. But another example is something like Z mod 25, right? That's another example of a ring in which it's not a field, but every element which is non-invertible is nilpotent. So let's call those kind of rings hyperlocal rings. So I want to run a similar divide and conquer program on the sphere spectrum. And let me see how would that look like. So we're going to think about elements as elements in homotopy groups. And for this, for a moment here, I want to consider if I have a ring in the world of spectra, and I have some f in pi d, how do inverting and quotienting look like? So indeed, if you have a ring in the world of spectra, you can define R with f inverted, and that would be and the homotopy group of that spectrum will just be the following colimit. So you're going to have contributions from pi k of R, but also from pi k plus d, pi k plus 2d. Oh, and we're going to take the colimit of this. So that's essentially what happens if you invert an element on a graded ring. What about quotienting? So, quotienting in this world behaves, closer to the way you're used to in homological algebra. So, if we're looking at the K homotopy groups R, of course, once again, you have an input from R, and definitely everything that comes from multiplying by f has to die. But this is not a short exact sequence as you have in classical algebra, but rather the sequence of homotopy group continues. So you have here pi k minus d minus 1 of R, and here you have pi k minus 1 for mod f. But other than that change, it kind of looks quite similar to the operations we have at our disposal in classical homotopy theory, in classical algebra. Sorry. So
maybe it's slightly different from classical algebra because this quotient no longer carries ring structure.
So yeah, that's a good point. I was kind of throwing under the rug, which is that in this case the residual ring structure is a little bit subtle. Let me ignore that point. It's not gonna influence very much what I want to talk about. But you're absolutely right. That's a good point. Other questions?
So ring is what some people call infinity ring, like defined using.
So I was vague on purpose. For what we're talking about, let's just say that the ring is just a spectrum together with a homotopy associative multiplication. Okay, that would be enough for what we want.
And homotopy commutative also.
Let's say homotopy commutative as well. Yes. This is a point in which I'm vague on purpose. I can say later why this vagueness doesn't actually cause any troubles. It's just a matter of technical precision that is there's a problem and the problem disappears anyway. So it's kind of one of those things in which, in a quick talk, dishonest people like me try to hide under the rug. So let's see. So let's look at this. Let's look at the sphere, and by sphere I mean the P-complete sphere. So what do we have? Well, there's nothing interesting happen in negative degrees. At 0, we have this local ring ZP. So this is not a hyperlocal ring. So we have a candidate for an element that we can invert versus quotient by, which is P in pi 0. That's one candidate. Or you can take powers of P, but P would do fine. There's also a lot of elements here in the positive homotopy groups, but Nishida proved, it's a theorem of Nishida, that all of those are nilpotent. So they're not going to help us to do this process at all. So we really have only essentially one choice, which is this P. So what does this suggest that we should do? Well, we can invert P. And because all of those are finite abelian groups, if we look at what's going to happen, we're going to find on pi star that we could just get a QP in degree 0 and 0 everywhere else. So this is a very, very, very simple piece, but also threw away all the information we cared about. On the other hand, we can look at the quotient. But then something very interesting happens. So even though before we quotient by P, the only element that we could, that is not nilpotent or invertible were P and its powers, up to unit, suddenly here we find a new element which is not invertible nor nilpotent. It's called V1, and for P odd at least it lives in degree 2P minus 2. So it all there's some things that I'm going to say that are essentially true and general and formally true only for P large enough. So here to say this degree P needs to be odd, but in any case there's something like that. Let's say in 2 it's degree 8.
But what about the ring structure, which is related to Moore space multiplication? I think there are some subtleties.
That's true. That's another subtlety. So here's one answer. There's different answer you can give, but one answer is that either let's just think about P large enough. In this case, P being free will be enough to talk about the ring structure, or you can take powers of P, and then the ring structure improves. In fact, relatively recently, Robert Merkland proved that the ring structure improves very, very quickly. So if you take something like P cubed here, this is already an E2 ring, for example, which is like way better than anybody ever thought. So in this, this process this geometric intuition, right, suggests that you don't care that much if you quotient by F or some power of F.
When you pass the powers of P, you also have to change your 2P minus 2.
That's true. That's true. Yes. Yeah. That's right. Star. So this is there's a certain kind of an asymptotic behavior here, and so okay, I was trying to kind of throw it under the rug, but let me say really what's going on. So what's going to happen here is that we're going to have elements, and we're going to want to quotient by them, and quotienting by them sometimes destroy the ring structure. But if you're going to quotient by some power of them, the ring structure is not going to be destroyed. So in some sense, the ring structure exists asymptotically in that direction, and we can always, at every specific case, take the power high enough so we have whatever good ring structure we need. And then those elements that I want to say, that I said V1 is in 2P minus 2, and these elements in general, they don't necessarily exist in the canonical degree, maybe only a power of them exists. and if I change this, then the degree in which they're going to appear might change as well. And also, they're not unique, but they are unique up some power. So there's a certain kind of, up to taking powers, everything is defined and unique as much as you want, but kind of you might have to change the powers to get any kind of specific level of well behavior. Okay, so that's the situation. Let me again try to go back and ignoring that issue. Okay, so we have this element which is not invertible and not nilpotent, so we can continue with the process. So we can invert V1 here, or we can quotient. And then suddenly there's another element called V2, and we can do it again. So that suggests a certain kind of inductive way for doing this geometric divide and conquer to understand the stable homotopy groups. And just notationally, we're going to denote this thing by T0, this thing by T1, this thing by T2. And again, those are, they're defined up to those choices that I made, but that's okay.
Is it difficult to give a definition of V1, V2, etc.?
So right now it is. Maybe soon I'll say something that one can say that will help me give it a more formal definition. I'm sorry?
Is T1 as simple as T0?
No. It's harder, and T2 is even harder than that. That's where I'm heading. Is this the thing that I need to? No.
On the left. Same on the left.
Okay. Okay. Good.
So in the co-limit, does the map go from n plus L to n plus 2L? Yeah.
It's k plus, I'm sorry, it's my handwriting, k plus d, k plus 2d. So you think about the elements here as elements of degree k divided by f, and here like elements divided by f squared. It's like denominators. Okay. What is true about those TIs, that if you look at their homotopy groups, they're always hyperlocal. So you can't break it any further. Okay? So let's assume for a moment that P is let's assume for a moment that P is, let's say, at least 7. So what I'm about to say is
sorry, maybe I missed some point. So somehow you say that there's a flexibility of raising powers of P and the V1, etc. But that the this T spectrum T depends on how you.
Yes, that's what I'm saying. I'm saying I gave it a name, and this is not really define it uniquely. In general, if I allow myself to change the power of P, if I allow myself to change this V1, I'm going to get a different T2. But this is, let's choose one, and let's make those choices, and then and then denote those by TIs. And in some sense, the different TIs are similar enough, so the analysis would be similar in all the cases. Okay, but those are not canonical. Okay, that's what I'm saying.
So something, do you always need to fix low-guided P, or it's not necessary? Like,
you mean here to quotient?
No, as a very beginning, like after I invert P, I got vanishing.
So if you invert P, you get this T0, and that's QP, right? And that's, if you want, this thing captures the non-torsion in pi 0 here, right? It's like there's non-torsion in pi 0, which is ZP. and it becomes this QP here. And then there's a lot that it doesn't capture, and that's it. Okay. Okay. So let me tell you a little bit about T1, just very quickly. And again, I'm going to do it in the case where I can actually quotient by P and get a ring, and that V1 is really in this degree 2P minus 2. Just to give some concreteness. So for these primes which are large enough, the homotopy groups here, well, it's P torsion, so it's a ring over Fp. And I have this element of degree 2p minus 2, which I inverted. So I get this V1. And then there's just another plus epsilon, and this epsilon is degree minus 1. Okay. So this is what we get in this case. And what do we learn from this V1 about the homotopy groups of spheres? Yes. Yep. So what do I learn about the homotopy group of spheres from this piece? Well, right, if I look at V1, I can look at V1 to the D. This belongs to D times 2p minus 2 of the sphere mod P.
So you're saying that P is greater than what? Sorry.
7.
So squaring of epsilon is automatic because it's...
Yes. Yes. Okay. V1 to the D, I'm sorry, for D greater than 1. So this thing belongs here. And now I have this going around map from over there to D 2p minus 2 minus 1 of the sphere. So this suggests that I can find P torsion classes in all of those infinitely many degrees. So we did get here some, rather than some kind of a low-level computation of the homotopy group of spheres, we found some infinite family. And we do know that this family doesn't vanish, and it's also essentially known under the name the image of J, or it's the P torsion part of the image of J. So this gives us, and this is due to Adams, essentially. So we do see that there's a way to go back from those hyperlocal things to the homotopy groups of spheres. Is there a question? I think I heard a question.
So you say Adams proved that this element is non-zero image?
Yes, essentially, yes. It's not exactly the language in which it's been stated, but yes.
And it is related to his J homomorph to...
Yes, if it's this element is also in the image of the J homomorphism. Always.
Okay, it is killed by P because it's...
Yeah, it's key. Yeah. Okay. So, okay, so we have all of those hyperlocal pieces, and we want to understand them, and hopefully then go back to understand the homotopy group of spheres based on that. And so, let's try to consider. Oh, I didn't really use the word very much. Let's try to kind of consider how did we use, how does those hyperlocal rings look like in classical algebra? And in classical algebra, right, what we have is we have fields, and we have those kinds of a little bit fattened fields by a little bit of nilpotence. And really what happens is that if I give you some hyperlocal ring R, right, then there's always only one characteristic, Fp for some P, where I'm allowing P to be 0, and then F0 is Q, such that this is non-zero. and it's 0 everywhere else, right? It's supported on a point. And then R admits a filtration whose associated graded is a module over those FPs, right? Like, so ZMO 25 is not the field F5, but it's built out of two pieces that looks like F5. So we can try to see if the same kind of phenomena happens here. Can we take those hyperlocal spectra and build it out of those some kind of residue fields? So for this, we need to analyze what are the residue fields in the world of spectra. And there's a, and what kind of characteristics they can have. So, well, it's one thing that you could do is just to say, well, we have this nice category, so we can talk about rings and we can talk about modules. And one defining characteristic of fields, or at least skew fields, is that those are exactly the rings over which every module is free. So we can use the analog definition in the world of spectra and define skew field in the world of spectra as a ring spectrum over which every module is free. And this gives us a lot of the possible fields, and a characteristic is not, there's a lot of different fields, like, F5 and F25 have the same characteristic. So we would like to find when two fields have the same characteristic. And in classical algebra, this is easy to see. Two fields have the same characteristic if and only if their tensor product is non-zero. So we can use the same kind of equivalence relation on these kind of fields in the world of spectra, and we get a very interesting thing. So, so we get that via this embedding that was mentioned before from a abelian group of spectra, we still have, the zero characteristic, and we still have this characteristic P. And let me ignore other primes. Let's say we were kind of under this P complete sphere, which correspond to FP. But there's now infinitely many characteristics interpolating between those two, denoted by P1, P2, P3, ... And this is now going to be renamed as P infinity. And the corresponding spectrum is what is called Morava K-theory. So, and Morava K-theory is a certain ring in the world of spectra that behaves like a field, and its homotopy groups. Well, okay, I only talked about equivalence classes, but in the same way that in the classical case, in every equivalence class, we have some kind of a prime field. In some sense, the same thing is true here, and we can get those, and they have a certain homotopy groups are FP. They join some class that we called Vn, which is inverted, and the degree of Vn is 2Pn minus 2. That allows me to go back and answer your question. So what the property that identifies this V1 is that if we think about this V1 as a map from this guy to itself, if we tensor it with K1, it's going to behave like this V1 here or some power of it. So after tensoring with this Morava K-theory, it looks like a power of this V1. And this is also why it has the same name.
So before you said that certain things are rings or EN rings, approximately you can make it as good as you wish by taking powers. And in the case of Morava K-theory, is it already good and for every P, or is it the same kind of?
So if you're only interested in it being associative, then it's good for any P. And commutativity is problematic. And for P 3 and above, it's homotopy commutative, but for P equal to it's not even that. But yeah, it turns out not to be a problem again. Okay. Other questions? Okay. So yeah. So those are going to be my residue fields. And
sorry, I missed some point. So you tensor K1 with what? Sorry.
If you take this ring and you tensor it with K1, you get a map, and this map is like you get modules over K1, so you can ask if a map looks like multiplying by V1. So
sorry, I'm a bit lost. I mean, it's tensor to K1 over what?
Over the sphere. Is that okay? Okay. So let's see. Let's try to push the analogy then further. Well, I want to think about those Tn's as hyperlocal rings. So in particular, I would expect that they will be supported only on one residue field, only on one characteristic. And this turns out to be true. So this is 0 if m is different than n, and it's non-zero if m equals n. So in that sense, those hyperlocal rings do behave like they're supported in only one characteristic. And so all of this picture is kind of, well, due to work of Morava and Ravanel, and essentially the proofs that everything works the way you would expect due to Hopkins, Devenatz, and Smith. And now we get to a conjecture that Ravanel made, which essentially is that the other statement is also true, that those hyperlocal things can really be built out of those residue fields. So the conjecture, which is known as the telescope conjecture, is that Tn admits a filtration in some sense suitable to this world by Kn modules. Which means that you can build those pieces, those pure pieces of the sphere, only out of those residue fields.
Sorry, by filtration you mean finite filtration or something?
I mean any filtration. I'm not even mean finite.
So it's Z-graded, right?
In a second I'll explain that it doesn't matter. It's false. So any filtration you cannot build it out of those kinds of things at all.
You need to say some convergence of the filter.
Yeah.
Yes. Okay. Let me be. That's okay. That's fine. If you close in the world of spectra this category into limits and dissuspensions, in a way that I'll explain in a second, this is not there. Okay, so that's what I mean, which is false. Okay, so it's kind of, yeah, we can choose what, you know, that's the level of strength that I mean. Okay.
So you close in the world of spectra using.
I'll say it. I say it formally again in a second. Okay, in a second I'll say it. Let me just. Okay, so, okay, you know what? Let's say this. So okay, so I can look in spectra, Kn local spectra. Okay, so this is what I get by closing under arbitrary limits from Kn. Okay. And so this is like Kn completion.
Limits are also colimits?
Not for colimits, but for omega 1 filtered colimits, if you want. This is not closed under colimits. It's like p-complete abelian groups. So you can close it under colimits, but you can close it under sufficiently filtered colimits. So this fully faithful embedding admits a left adjoint, which is known as Kn localization.
That should also contain everything that admits any Kn module structure, right? I mean, so that's.
I'm sorry?
And you should include some colimits, like an infinite direct sum of Kn should also be in there.
Well, it directs. Well, if it's closed, this is a stable category, right? If it's closed under finite limits, it's closed under finite colimits.
Yeah, but an infinite direct sum of Kn should be in there.
Yes. Oh, you're saying if I just say limits, I don't get that for. Okay. Yes. It's closed under. Well, the infinite direct sum, which is countable, is actually not in there. I need to. No, that is in there. I'm sorry, but if you close it under all limits and omega-1 filtered colimits, you get that category. So I was kind of trying to be non-technical, but that is a correct. This is a formally correct statement. I'm quite sure.
Sorry, are you starting with Kn or are you starting with an arbitrary Kn module?
Arbitrary Kn module.
Then there's no problem.
Yeah, I'm starting with an arbitrary Kn module and I'm closing under all limits and omega-1 filtered colimits. I'm going to get that. I was trying to try.
And final and suspensions, the suspensions, and
Well, those are.
That's going to happen for free now, but yes, add them as well. Okay, so we can approximate every spectrum universally in this way. For example, Tn. And an equivalent way to describe the telescope conjecture is that this thing is an equivalence. Okay? So for n equals 0, you see that this is evidently true. We just get QP, which is definitely a module over Q. Right? For n equals 1, at least for these larger values of P, this thing seems to be very suggestive. It seems like there's two pieces of K1 here. So one might think that that's would actually work. And it does. So for at n equals 1, this conjecture is true. It is not obvious. It was proved for odd primes by Miller and for p equals 2 by Mahold. And then, so Brooklyn. For n bigger than 1, this is false. And all prime. Okay. So this is just false. So here's, I think, what would be a very natural question to ask. Who cares, right? So I kind of pushed this analogy that I was trying to say that it's a good analogy between spectra and abelian groups, and we walked hand by hand with them, and then I tried to show you that more and more things are, by this analogy, the predictions are correct, and then we have the main prediction I wanted to say, and the theorem that the prediction doesn't work. So what is that good for? One reason that we should care is that the way that we show that this is false actually teaches something about this Tn, and in return teaches something about the stable homotopy group of spheres. Okay. Okay. Well, one thing that you can prove about this Kn localization of the Tn local of Tn is that it has finite homotopy groups. All homotopy groups there are finite. So one way to disprove the telescope conjecture is the following statement that follows from the way we disprove the telescope conjecture, but uses a little bit more input. So this is due to Berklin, Carmeli, Hahn, Levy, Sepenkovsky. which is that in fact pi 1 of Tn is infinite dimensional. It's an infinite dimensional FP vector space. In particular, this map has a large kernel on homotopy groups. So okay, a little bit short on time. Okay, so I'm in the very little time that I have left. Let me say two things about this. So one is what do you learn about this from the stable homotopy group of spheres? Well, if you go through what does it mean to quotient twice, right? So this thing is, so let's take the case 2. So that would be the sphere mod P mod V1 V2 inverted. And if you go through what does it mean to quotient twice and then V2 inverted, the fact that you have an infinite dimensional vector space implies the following thing. So we can look at the P rank on the K stable stem, and this jumps a lot. So let's smooth it up a little bit, and then if we do this a little bit of averaging, from this you deduce that this thing goes to infinity as n goes to infinity. So it already gives you a lower bound on the how much the way that those stable stem grow. Note that the original thing that we had with this image of J only told us that this is bounded below by some constant, by some specific constant.
What is rank P? Is it the...
Sorry?
The rank P is the dimension modulo P or the...
Yeah. Dimension over FP mod P. Okay? And in fact, so this is a work in progress, but I think, I'm fairly confident. In fact, we can show that it grows kind of larger than a logarithm by additional methods. So where all of those classes come from, right? So, I told you, okay, I have a bunch of classes here, they die here. So there's kind of two questions now. One is, where do I find those classes? And two, how do I know that they're not zero somehow? I'm constructing them somehow. I'm going to have candidates, and then I want to know that they don't die. So those classes comes from the following following observation. So, I started. I erased it, or no, it's over there. So I said that we can think about a spectrum, some kind of a space, so that every time that I have finite set, I can sum over it, over a function. But so based on the work of Hopkins and Lurie, together with Carmeli and Janowski, we proved that in fact, for those spectra, when those spectra is Tn, they have an additional structure. They have some kind of a measure that allows you, for certain spaces, also to compute the sum. Or because it's a space, we usually denote it by an integral. Those are the spaces that has finitely many finite homotopy groups. So for those kind of spectra, it's not only that if you have a map from a finite set, you can compute the sum. Also, if you have something like a map from B Z mod P cubed mapping, you can compute its integral. And by doing these kinds of computations, we can produce all of those additional classes. I don't have time to say anything about the way we detect that they're non-zero, but essentially, let me just say that we do it by mapping to some well-chosen spectrum, which is constructed using K-theory. And I'll stop here.
Thank you, Tomer. Are there any questions?
I was not, I'm complete layman, so those Morava spaces which are crucial in definition, V1, V2, etc. Could you briefly explain to me?
Sure. So there's a sequence of spectra indexed by a prime and an integer, but we fix the prime, so we suppress it from the notation in this case. They're ring. They have this associative ring structure. And well, on the level of homotopy groups, their homotopy groups look like so, as I said. Let me give an example first. So what is K1? Well, there's this one way to come across spectra is as representing cohomology theories. And we can take the spectrum that represents a complex K-theory, Ku, and quotient it by P. That would be K1. I'm sorry, almost. Okay, K1 is a piece of that, is a retract of that. Generally, the way that those are defined, usually, there are different possible strategies, but one way is you take complex cobordism, and by Quillen's theorem, you know that the homotopy group of this is some big polynomial algebra, and then you take appropriate quotients and inversions until you get Kn, and then those special properties that Kn have, that they behave like residue fields and all possible residue fields, is essentially the content of the nilpotence theorem of Hopkins, Levy, Nuts, and Smith. So I hope.
Thank you.
Yeah.
So I have a quick question. So
Yes, the person who raised their hands in the back.
Yeah, thanks. So I was trying to follow somehow these kind of the operations of spectra which you described. So apparently it's possible to do arithmetic with spectra just like you can do with rings or so. That's somehow, I think, one of the points of your talk, right?
Yes.
And so I cannot understand. Can one make explicit what is like quotient of spectra or something like that? How do you do that explicitly?
Well, explicitly you mean in the model that I mentioned above, in the original model. So okay, so here's something that you can do. So if you have a map of spectra, okay, so describing the cofiber, describing quotient, a priori seems a little bit weird, but there's something which is very easy to describe kind of naturally, and this is a fiber. So you can just take the fiber, if everything has a base point, and you can just take the fiber on every level, and if you take the fiber on every level, it's because of the way this loop behaves, you see that this is still a spectrum.
And you mean homotopy fiber, just to...
Yes, I'm sorry, homotopy fiber. But now there's a little trick. So, spectra behave like complexes. So the cofiber is just a shift of the fiber. And you can shift just by re-indexing those xn's. So that's an example for a formal, this is a formal model for taking a quotient.
This is also the quotients, like when you're writing slashes in your talk, this is this kind of quotient.
It is exactly this kind of quotient.
Yes. Thanks a lot for your explanation.
Yes.
So when you do it with n, with like sphere spectrum and a prime, you get the sphere mod P. But again, like we said, that it's not a ring. No, you said that. Okay. This was addressed in your.
Yeah. So the observation. Okay. So here's the two things that kind of can calm you down a little bit. So one of them is that the level of ringingness you need in order to invert and take quotient are just that an element in the homotopy group will induce multiplication. So you need very little, right? You just need the product, which is, you don't need that much. But of course, if you want good behavior, you want maybe this product to be sufficiently associative or sufficiently commutative, et cetera, et cetera. As I said, in those lower level it appears in some concrete level, and everything gets improved when you take powers. So there's somehow there's never a real issue. So it serves more as a technicality in this story than something which is really affects the general picture.
So remember in Thomason's work, for the prime 3 it passed to 9, for 2 it passed to 16 to get his.
If you want to do certain explicit maneuvers, then yes, I'm not saying that it's not important. I'm saying that it doesn't affect the general picture. So for if you want to prove things or do something concrete, sometimes you need to do this, but the general picture remains. So if you can, by replacing things with power, you can just pretend that things are rings, and as much as you want, and that it works out. And in a concrete case, sometimes you need to grapple with the effect.
So does this story tell us something about unstably? I mean, maybe in combination with some work by High-Hoyt or something.
This is I wouldn't say so. High did a lot of he did a lot of work about unstable homotopy groups, the way it's related to the telescope. But his work is somehow a little bit less directly connected to the actual homotopy groups that you see here. But there is a process called the EHP spectral sequence that does allow you to move information to some extent from the stable to the unstable world. There's nothing kind of very direct that happens in this specific case. But that's if you want to go on the level of homotopy groups,